I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day.
Oh, come on outside, ladies and gentlemen, boys and girls. What you're about to see is out of this world. Step right up now, don't be shy, because we're about to show you how cars can fly.
Who dares to fight with the icon of his day, and she finds her own miracle on the way. I said, hey now, life's a joy. You gotta try your best and give your all, and when the facts don't fit the theory, change the facts again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. It's a beautiful day.
5, 4, 3, 2, 1. Silence. Good morning, good morning, good morning. I'm Dave D. Hilstrom. You've reached our Saturday Science Chats. I love that music. In the beginning of my countdown, I put that in there. Michael Ruggieri, the composer and lyricist for that actually soundtrack and actually a theme song for my documentary film Einstein Wrong. Have you seen it? EinsteinWrong.com. Take a look at it. It's a really entertaining film. But he's going to be here tonight. I haven't seen him in a while. We've got another crazy and wild project we're going to do. We're going to take Einstein Wrong to even bigger heights. That's years in advance. But today we are really lucky to be talking to a person who's been working a lot on a new theory called the Scalar Theory of Everything. But before we do that, of course, we're going to take a look at some news and tell you who we are. But stay tuned. It's going to be really great. It's a really interesting theory. And, of course, we are critical thinkers. This is where we meet. We're the John Chappell Natural Philosophy Society. And, of course, the science, Dissident Science News Channel. I want to thank all my subscribers and everybody. Wait a minute. Did we pass something? I think I did. That's the problem when you hit all the wrong keys. But I was going to say, I'm having to talk about something that I didn't. No, here we are. But anyways, thanks to all watching, especially if you are a member of the John Chappell Natural Philosophy Society. We are growing. Thank goodness for all of our work we're doing here on Saturdays and everything we're doing on the internet. And I want to thank all my subscribers, Dissident Science. We're getting close to I don't know, getting close to 4,000 subscribers, and I want to thank everybody who has subscribed. And remember, folks, just go down there, and if you like the content here, click on the like button and also the subscribe button, and click on the little bell. If you put it into the right position, you'll get all the announcements when we go live. So support us that way. But I want to thank everybody who's watching both live and in this recording. It's greatly appreciated. Without your support, of course, none of this would be happening. And again, we are where critical thinkers meet. We're the John Chappell Natural Philosophy Society, and we use natural philosophy in a broader sense, which includes physics, cosmology, mathematics, and philosophy of science. Our goal is to return to the basics where things went wrong and start anew. Our mission is to be an organization above all that promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside the mainstream, like what we're going to do today, and to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, and other topics, to provide a forum for presenting serious papers and theories without fear of censorship, and to be run and controlled entirely by our paid membership, and that's really important. Who we are open to challenging challenging mainstream science. We encourage competing ideas or models. We also follow the scientific method. A lot of people think, oh, you guys just throw out all this. No, come on, guys. We're like everybody else. You got to follow the scientific method. You got to describe all data that's out there, and maybe even more data that other people can't describe. That's normally what happens in new theories. And you can consider an idea without accepting it. That's who we are. That is, we can listen today and listen to John and his theory and consider that idea. We don't have to accept it, but we can consider it, and that's the whole idea. I always enjoy new theories and new models because people have worked many years on them, and it always opens my mind to a lot of different things. We also give voice to the voiceless. This is where science advances, and always has. That is, it's always outside the mainstream. Mainstream is always stuck. It seems like somebody on the outside has to come in and shake things up. Of course, who we are not, as one of the things I've been putting up more recently, is we're not a specific point of view. That is, we don't have an organization where we all subscribe to a theory. Everybody is here to discuss it's science and trying to fix science, but we do not have a specific point of view. So if you believe in one type of model versus another, it doesn't matter to us. We accept everybody because this is the way science should be. Science should be like all other businesses where people brainstorm and try to come up with different ideas, and the winner will be chosen not by us but by history. We're not a new age kind of group. We're not a general science organization. We don't talk about everything in science. We pretty much stick to physics and cosmology. We don't take the time and talk about conspiracies or UFOs either. We really we stick to the fundamental science like light and gravity and fields and magnetism and all that, because we don't know really what they are. So let's start with the basics before we get all a new age on everybody. So that's at least our organization. We do have websites, the sciencewoke.org website, online magazine for critical thinkers, really great magazine. And we have also naturalphilosophy.org, critical thinking. It's our critical thinking community. That's where you are going to find all the people in our organization talking to each other and conversing about topics that are really interesting. You can join up. It's really easy. It's free to join. We also have our Wikipedia, which is a natural philosophy Wikipedia. It is closed to the public because if you open it up, it becomes the consensus, and anybody's ideas that are not the consensus, they get thrown out. So we have over 10,000 pages in that, so you can want to check that out. We do have memberships. It is very, very important. We just got a bill for $300. For what? For security. What? Well, let's put it this way. We had our websites and our databases on my own server which I donated for about 5 years, maybe more, and we were hacked constantly. In fact, a group anonymous from Brazil even announced on our webpage at times, you've been hacked by anonymous from Brazil. There's a couple of reasons. I won't get into them. I used to live in Brazil, so they thought that was funny, I guess. But since then, they do have companies now that will help with those things. And because we do post things that go against mainstream, and I'm not talking about that hurt anybody, we're just talking about different ideas, we are a target. So we spend $300 a year, $299 a year for a company who watches our server like a hawk, and we have not been hacked since. And is that worth it? Yes, it is. And how do we pay for that? Well, we pay it for monthly dues, memberships, annual memberships, and donations. And we get all of those. We have people who are on their monthly memberships, so $5 a month. That's all. It's like $60 a year. Helps pay for this. Our expenses come to a couple thousand every year, and we do have annual memberships, which are some of our the way we did it before. Annual memberships of $35 if you're retired, $50, $100, $200, etc., all the way up. And we do get donations, and that's really important, and that really keeps us going. In fact, our patrons. Are these people who have donated generous amounts of money in the last couple of years. Dr. Cynthia Whitney, our chief research scientist, she's got her degree from MIT in Special Relativity. Nope, she doesn't believe special relativity correct, even though she got a degree in it, tried to apply it and didn't work. Nick Percival, another great mind. I think he graduated from Harvard. His generous donations, entrepreneur he is and has helped us out. Duncan Shaw, who has what I call the Vancouver ether theory, really interesting theory, publishes all around, also in our proceedings. We have an anonymous donor. I want to thank him. He doesn't want to be mentioned. And also my father and Kurt Renshaw, a couple of people that have made donations, and it is greatly appreciated. Most of all of these are, well, they all are actually members. The CMPS 2021, we will have a conference. If you are interested, please send your accepting papers for proceedings at naturalphilosophy.org. We put them together in a book, and we will be having an online conference in the fall. We're going to have a pretty good forum there. We're going to have presentations, and we're going to have those presentations will be available for people to watch ahead of time. I think that's going to be the best way to do it. And then we're going to have like Zoom calls, basically, so that everybody can get in and discuss them just like we're in a room, which I think is going to be pretty cool. And so you don't want to miss that. And we will have our official launch this month. Hey, Dave, when you're going to put an extra day in the week. As soon as they get 8 days in a week, I'll be able to help this. But if you are interested in helping out, please contact me. It would be greatly appreciated, any help. We also are publishing. We are ready to publish Notfinity and also a book on ether. And we are out to our first reviewers on Principia Mathematica 2, my father and I's book, A Model of the Universe, completely Newtonian, only 3 dimensions. Can you believe that? But also, our community news. Guess who registered, who's been away from us for many years? Now, I don't know how much he's going to participate. I saw this Greg became a registered member, and that was like an hour and 2 minutes ago. I don't even know if he's like in anywhere, but for lots of you who know Greg from the days of the MPA and the CMPS, he is an absolutely wonderful human being, extremely intelligent, has his own ideas of the universe, but I really enjoy him. He is my best bud when it comes to science, and I've been in contact with him. They're actually digitizing all kinds of work from dissident scientists, people working outside the critical thinkers working outside the community. He has been digitizing that with his son because he has literally like boxes full of this stuff. I guess there was some monies to be able to do some digitalization, and they're actually being digitized and destroying the papers because how can we keep them? But we'll have the digital records of everything. What we do with them is another story. Again, that's why it would be really great. So any millionaires watching this who want to help our organization out and donate money to help with these things, let me know. It would be absolutely great. Anybody's help. Also, some more community news. We are having discussions all the time there. And one of the latest discussions was talking about the science woke, and the word woke. Some people like me, I don't have some bad connotation with it. People have made that into a bad connotation. We're thinking about critical thinking. What do we call that? Do we change Science Woke magazine? Well, we've got Nick and Dieter and John, Eric, all members chiming in on what they think. So you want to put your 2 cents worth in? Get on our website and we'll talk about, should it be sciencewoke.org or something new? What else? Oh, we have, I always put up there, just having my dad put out a video, 3 forces, not 4, if you haven't taken a look at it. It's a lot of fun. His last videos have been quite interesting. The speed of electricity, the speed of light, the speed of magnetism. Is that right, Dad? Shake your head, yes or right. No? What was the speed of something else? Okay. Anyways, you have to go and watch it. He has had a really great series, I think, on some very interesting questions in physics, but you want to check that out. I'm going to move on and play coming attractions. Here we go. Yes, sir. We've got more people coming. Of course, we have the finite theory coming up. Hopefully, that will be very soon. Just like we're looking today at the Scalar Theory of Everything. This is with Phil Borkert. I know that Nick has been working with him. Also have Disruptive. I think that's be coming up in May, actually, talking with him. Really great mind, super articulate, way more articulate than me. This guy can get up in front of, CEOs and talk, but really super guy. Love his work. Disruptive, Rewriting the Rules of Physics. If you haven't got it, you can get that online. I think Amazon has it. Take a look at it before we talk to him about it. Then something else coming up is Thomas North and Shakespeare. It's some really interesting using some machine learning, some of the algorithms today, looking at the text, comparing Thomas North with Shakespeare, finding out that Shakespeare did use quite a bit of North's work. And it's always interesting. Dennis McCarthy actually gave a talk. If you look up Dennis McCarthy and the NPA, or on our channel, if you look him up on the Natural Philosophy channel, you will find that he gave a talk about 5 years ago, I think, about flora and fauna and expanding Earth. Yes, he is an expansionist, really great mind, really love Dennis McCarthy and his work, always thinking outside the box. And this is sort of in the tradition of Domina Spencer, who was one of the presidents of NPA, one of the great minds. She got her degree in mathematics from MIT, and she would bring in people sort of outside of physics and cosmology once in a while to talk about some really interesting critical thinking work, which kind of opens our brains up a little bit more. It's sort of get people out of the rut of only thinking about physics and cosmology. So I think this will be quite interesting. And of course, the time zones have shifted. It's all Dr. James Maxwell's fault, because he is, in my opinion, the most important geologist ever to live, in my opinion. And his work with expansion tectonics, which he actually coined. It was his fault. I always blame him for the Earth expanding more in the Pacific and making him live so far away from us. But the time zones have favorably shifted for Perth, and I believe he can at 10 at night until midnight. It's exactly 12 hours difference. He'll be able to present. He says, Dave, I've got another presentation, and his stuff is always fantastic, so you don't want to miss that. And of course, are you next? Are you going to sit here and put up with the physics police? No, the physics police is for the mainstream, not for you guys. I'm a supporter of everybody's work, and you can be next if you have something. You can contact me. I've had numbers of people contacted me, and we are I'm looking at those things to see if we do want to present. And one of the people today did contact me, and we are going to play today's bumper. Yes, we're going to have him coming up, but let me tell you a little bit about it. We're going to be talking with John Hodge today, and we'll be bringing him up. I see he's ready in the green room with other people, and he is purporting a scalar theory of everything. A little bit history about him before we bring him up. He's got his Bachelor of Science in Physics from Rensselaer. I'm a linguist. I can't read, but from a Polytechnic Institute, and he has a Master's of Science in Physics from Georgia Institute of Technology. Hey, go Bumblebees. I think that's what it is. My company works actually a lot with that. It's a very well-respected technical college. Well, it's a university, like MIT, in my opinion. And John sold his electronics company in 1991 at age 49, retired. I guess then he said he retired from retiring and has become an inventor and amateur astronomer. His interest is in cosmology. His interest in cosmology developed then. He conceived the new cosmological model in 2002 and started publishing papers instructing at the Blue Ridge Community College, corrupting young minds to think outside the box. How dare he? And then after writing The Theory of Everything, Scalar, his interest turned to philosophy. So one of the things is why I thought I'd put this up before we bring him up. Why are we looking at new theories? If there's 17 models out there, well, it turns out that mainstream science is is in my contention, and this is my thesis, that we are in model revolution. Thomas Kuhn and paradigm shifts and the the Revolutions in Science. If you have read his book, I absolutely believe we're in model revolution. The model was broken apart. It wasn't relativity. The relativity was the data. We're looking at a theory that's breaking down. Then we have a lot of data that doesn't fit relativity. Obviously, our chief research scientist of our organization, she got in the late 60s, got her degree in special relativity, went to apply it with ring gyroscopes, and it failed. So if relativity is so good, why does it fail? And then her professor says, well, we all know it, but what can you do? So the new theory has to break apart. Then you got to get enough data that there's so much data out there that it can support numerous models. And that's where we are right now. That's why you see so many people. If you haven't seen my video on the model revolution, look up Dissident Science Model Revolution. I put together a really nice video on this, about 16 minutes, well edited, graphics, the whole thing scripted. Take a look at it, and I think most people are agreeing with me that we are in model revolution, which means we have to look at a lot of different models, because a lot of different models are fitting the new data that's out there. Of course, new theories and models open our minds to other possibilities. That's why it's important. And you never know whose theory is going to stick, so us to be the judge of that, we are not the judge of that. So what I'd like to do now is bring on our guest before we take a look at his video. He's got a video presentation, and we'll bring him up. I want to say hello to John Hodge. Hello.
Why, hello.
Well, it's great to have you on here, and I know you had contacted me. Where are you coming from in the world, since people are watching from around the world here?
North Carolina.
North Carolina. All right, that's not too far from me. North of me. And tell the audience a little bit before your video. We play your video and your presentation. How you came about this? Why would a person with an electronics company sell everything, retire, and then all of a sudden start working on a theory of the universe? Give us some insight to that.
I'd been interested in such things.
Oops, we are glitching on him here. Hello. 1, 2, 3. Okay. He has seemed to have stopped. So this happens, folks. We all know this. Everybody who lives in the world of Zoom, as we say. I don't know. I think he looks frozen to me. He's frozen to everybody else in the green room, yes? Yes, okay, he's frozen. So that's okay. We're going to see if we can get him back. I'm going to bring myself back up here and bring him down. And maybe, hello, Dave. Press the right buttons here. Let's see, remove them. There we go. I'm back. That's what I get for. So, John, if you are watching and hearing, you are frozen. So maybe you want to come back in, and go out and come back in. That's what he has done. So we're going to be talking. We're talking with John today about the Scalar Theory of Everything. We do have a video for that. Let me get that all sort of ready here, and we will watch that. So we're gonna see if he can get back and talk with us a little bit. Get back with us, and if not, then we'll take a look at his video, and then we'll discuss it. So let me make sure I am ready for this and his video here. So there we go, and hopefully he will be back here soon. We'll give him a minute or two, but if not, again, I will go ahead and let me remove this. Get this ready, stop my screen sharing, because I'm going to now screen share, and we'll watch his video here while he gets back. So we'll do that, and yep, I don't see him yet. So we will watch the video. I'm going to get this up here. I think I forgot to put in the audio. So let me do that, share screen. It's got a check mark for the audio. That's what I will do. And we should be good now. And here we go. So we will go ahead and start this. And people in the green room, please give me a thumbs up to let me know that, in fact, we are sharing, and you are hearing the audio. So if I see thumbs up, I will pull out and we'll take a look. This is the Scalar Theory of Everything by John Hodge, paradigm shift and causal model of the universe.
The scalar theory of everything is a paradigm shift and a causal model of the universe. This is the paper.
Is it low? You're not hearing anything?
This video.
It's low.
starts
Okay,
with the
okay.
foundation.
Okay. I think it's actually low, unfortunately. That's the highest I can get it. Okay. Well, I guess we're going to have to listen in. Turn up your volumes, folks, because I've got the volume on max there. So I do hear it, and I hear it okay, but of course I've got my earphones on. So hopefully we can please bear with us. And I'm just going to see. I don't even know here if I can take a look. And let me bring this down here. Again, we're with John Hodge. Let's see if we can bring him back and see what he's here. Hey, John, how are you?
Hi, fairly well.
Okay, why don't we get back to the question, which is how did you get in all this? And while you're doing that, I'm going to see if I can get this volume up on this video, okay?
Well, I've
Go
always
ahead.
been interested in physics. I did hire for a company, worked for TI in their research labs, ended up owning a company, sold it, then started looking at my original interest, which was cosmology. Late in the 1990s, I came across the quasi-steady state cosmology model and figured that was better than general relativity. So I went the next step, which was to add a sink to the QSSC and started solving problems. The STOE is broader, as you will see, simpler, just like Tom Kuhn likes.
Right,
So
right.
Here I am.
So how long have you been working on this particular model?
Two answers to that. One, since I was a teenager, since I always kept it in the back of my mind, but intensively since about 2000.
Okay. 2000, 2002. Okay. And you made this video not too long ago. So this is really your first foray to actually spreading the word. Have you written it down? Have you published? Do you have a book?
Well, originally, back in around 2002, 2003, I was attending the standard conferences, and I've been published in a peer-reviewed journal, but they soon kicked me out. The model was too extreme for them, I guess. Then I published on the archive for a while, and they kicked me out around 2010. So now I'm with what's called Intellectual Archive. I publish there because they distribute abstracts to libraries, and they go on Library of Congress, and they now have DOI kind of linking. So I'm publishing, but you know, the thing with being rather radical is that you don't get too many people to listen to you. So, you know, that's all right with me. I just like doing the work.
Right, exactly. Okay. Well, and tell us a little bit about the presentation people are going to see today.
Well, it's a general summary of the scalar theory of everything. It starts off with the general postulates of the STOE, and then it goes into various first cosmological problems in current models, solves them or shows you the solution in the STOE, and then goes into the small words by means of looking at light and diffraction of light. It's a particle model of light, which means the problem is to solve for the interference issues.
Right.
Then later on, there's some additional work which is rather speculative. You know, it suggests that there's only one force, a magnetic force, and all the other four forces derive from that.
Gotcha. Okay, well, that's good. So I'm going to bring you down. I think I've solved the volume problem because I think I have my volume low because I have my earphones on. So I appreciate you coming again. I'm going to take you down here and we're going to take a look at the Scalar Theory of Everything by John Hodge and his presentation. So everybody in the green room, let's see if this now is going to be better volume-wise. I think I put it up as max as we can here, okay? So please, people watching, thumbs up or thumbs down on the volume.
The scalar theory of everything is a paradigm shift and a causal model of the universe. This is the paper. This video starts with the foundation, forms a universal equation, applies the equation to the current observational problems. These are, I calculate a theoretical universe temperature, which no one else does. The galaxy rotation curves are still a problem because the dark matter has not been found. Asymmetric RCs are a problem because nobody knows why. Galaxy redshift because the correlation coefficients are very poor. Periodic redshift, again, no model. The Pioneer anomaly has 10 characteristics, of which only one has been explained. Planet 9, they're still looking for it. Coherent light for particles, which has not been done before. And a model of a photon, which gives us diffraction. The transparent mass experiment, which rejects wave models of light. And gravity is the asymmetry of the magnetic field and some others. I start with Newton. Newton established a major physics advance that was confirmed by predicting the late return of Halley's Comet. Newton identified three characteristics of bodies that have been identified as three characteristics of mass. After Newton, then I examined experiments and observations without intervening models. For example, I don't concern myself with Doppler shift for the galaxy. It's a galaxy redshift, not a Doppler shift, if you see the difference. I form a model to explain all the universe. Postulates that the stuff of the universe is continually being emitted through sources at the center of spiral galaxies and ejected through sinks at the center of elliptical galaxies. The stuff of the universe are Hodge, which are discrete magnets that cause a depression in the plenum. They are two-dimensional. Plenum, which is like an ether, continuous, that supports wave actions, and the interaction of the Hodge and plenum. Matter bodies are emergent assemblies of Hodge and plenum. The huge issue facing physics today is that the foundations of the big, the classical, and the small size scales are inconsistent with each other. The STOE is justified because it corresponds to all scales. The model many of the problem and has made predictions which were later observed. The three characteristics of mass, or bodies. Weight. The plenum force acts on the surface of the Hodge. The inertial mass is the property of the plenum required to support waves, and gravitational mass is the effect of Hodge on the plenum. A body has Hodge held in place by the plenum. Newton's model works by defining forces that are exerted on bodies by an ether, then adding forces vectors to arrive at a single force that predicts the body's measurable motion. Note, forces, not energy. Newton suggested a reductionist step in theory by positing an ether whose divergence exerted a force that caused gravity and that caused diffraction, and by positing corpuscles as light as components of matter. That is, support for the ether and corpuscles was because the model could explain several diverse observations, then known but mysterious, rather than by direct observation. Today, this might be known as a theory of everything. I started the STOE by returning to Newton's path and then jumping forward to the quasi-steady state cosmology of Hoyle. This is the reference. The QSSC suggested a source of the stuff of our universe at the center of galaxies. It solved the rotation curves of spiral galaxies and other current problems. This is the cluster structure according to the STOE. We have source galaxies, elliptical galaxies, sources and sinks. Sources emit plenum and hods, which then form hydrogen, which then flows outward from the spiral galaxies. Some of it forms suns and flows back inward to nova. The iron core of the nova then forms black holes. The black holes fall into the center of the spiral galaxies. Now the plenum density is very high, and this crushes the black holes. And this is seen by X-ray bursts, which are unaccompanied by other radiation. These have been noted, they have been connected to black holes, but people do not still understand what these X-ray bursts are all about. Another output of the nova is heavy elements, rocks, some of which go back in as solar systems. Others flow outward to the inner galactic space and then flow back into the sinks, where some of them come in hot, they flow out, they cool down, and they flow back in. This is the observed cooling flow. This is the cluster structure. We have spiral galaxies around the outside and elliptical galaxies in the middle that are sinking all the matter that these spiral galaxies are emitting. Binney and Merrifield for a description of galactic astronomy. The universal equations formed. This is the plenum density at some point. You'll notice it consists of components from the source, the sink, and matter. The numerator here is the strength of the source or the sink and the gravitational force of the matter, of the Hodge. You'll note they are all inversely proportional to the radius. That is, it's three-dimensional space, not four, 3 dimensions and only 3 dimensions. The rho, the divergence of the rho, dot product with the normal of the Hodge surface forms a force on the Hodge. The force on the Hodge divided by the inertial mass of the Hodge then gives you the acceleration. You'll note all the universe causes the force or directs the path of a dropped object. This is a Machian theory. It is a causative theory. This looked at the B-band luminosity of sources divided by the B-band luminosity of sinks within some distance. And we increase the distance. And you'll notice that as the distance gets around 150 megaparsecs, the ratio here approaches 2.7. This sets the constants in the previous equation. The STOE also accepts a negative feedback principle. That is to say, fine-tuned parameters are controlled by a negative feedback loop. The problem is finding the physical feedback loop. For example, universe temperature seems to be fairly finely tuned, and this is of the microwave background radiation. Now you note I said microwave background radiation, not cosmic. No proof exists that it is cosmic. The source increases heat, sinks decrease heat in proportion to the mass in the elliptical galaxy. Heat of the galaxy cluster, heat in, heat out. Apply the heat equations. This is the long-term average temperature, and you get this curve. We are approaching the long-term average temperature, which works out to be the Euler number 2.718. if you look at the mass time it takes to flow from the source galaxies to elliptical galaxies, you can calculate that to be at about 5 billion years ago, and that at about 14 billion years ago. This is increasing temperature of the universe and increasing volume along with the increasing temperature. Rotation curves. The focus has been on flat rotation curves in the outer part of some spiral galaxies, but rising and falling rotation curves also exist. These are falsifiers of dark matter. There's my paper. Asymmetric rotation curves. This is the rotation curve in the outer part of the galaxy. Some continue at that velocity. On the other side of the galaxy, the rotation curve continues at a slightly higher velocity. That gap right there is known as an asymmetric rotation curve. 20 years ago, there was quite a lot of investigation into what causes the asymmetric rotation curve. They didn't come up with a model, so these days, they don't really talk about it too much. What happens in the papers is they just simply average the two sides and say that's the rotation curve. The three forces acting on matter outside the center of the galaxy. Here's the rotation velocity. This is the inward force of the gravity. This is due to the luminosity or source strength, and this is the force exerted by a neighbor galaxy. I use one neighbor galaxy on the matter in the target galaxy. The results. I sampled 105 spiral galaxies, which is all I found. That is to say, I didn't choose any galaxy, only what others have chosen. 16 had Cepheid star distance calculations, which are very accurate. 49 of the sample have published asymmetric RCs. The little dots you see in some of these are the data. The lines are the STOE calculation. In the dark matter hypothesis, you go from a declining rotation curve, which should be Keplerian and normal Newtonian. You add dark matter to that kind of a curve, and you get a flat rotation curve according to the dark matter hypothesis. But how do you then get a rising rotation curve? Well, you get it by adding more matter. The difficulty is this galaxy and that galaxy are known as low surface brightness galaxies. These have less matter than the average, and therefore this is a falsifier of the dark matter hypothesis. Here are the equations for 4 galaxy characteristics. This part is the target galaxy characteristics. There's the neighbor galaxy, and you will see that the 1 sigma uncertainty level is very good here, 5%, 2%, 3%. This is very good. Now, galaxy central mass and central velocity dispersion have been found to be related to outer galaxy parameters. The difficulty here is the accepted model, that is to say the infall model of the Big Bang theory. Matter flows in, but we see that hydrogen and other stuff flows out, so in spiral galaxies. So according to the standard model here, then there should be no connection with galaxy central mass and central velocity dispersion. The STOE holds there is because from the center comes the rest of the galaxy. B-band luminosity has been related to these outer galaxy parameters, and so I look at it, and I find that there is a very good relationship between the two, the same as before. Target galaxy, neighbor galaxy, and the 1 sigma is 6% and 3%. That's very good. Galaxy redshift. This data is from the Key project. They use the Doppler shift to determine the redshift theoretical value. They calculated a Hubble constant of 70 kilometers per second per megaparsec. So here we see their theoretical or calculated variable versus their measured redshift. This correlation coefficient of 80% is poor. These galaxies are within our cluster, seem pretty good. These galaxies are from another cluster, and that is not so good. 80% overall is poor, considering what this Hubble constant is and what the Cepheid variable distance variable stars is. It's the base of the astronomy distance ladder, and it's a base in the Big Bang theory. It's very important to have a correlation this poor. This is the STOE derived equation. There's the redshift. I have 5 constants, but I have 32 galaxy data points, so it should be pretty good to get that. The D, P, and F are characteristics of the plenum along the line of sight as the photon from the target galaxy comes to us. Those characteristics then modify the photon. And here's my calculation. I have a correlation of 88%, which is much better, but even so, I have that one and that one and that one being galaxy outliers. And this is perhaps not too good to have outliers like that. Halton Harp, in his book Seeing Red, suggested quasi-stellar objects are actually new spiral galaxies closer to us than what traditional science thinks they are. If you add these back in, the correlation goes to 93%. I recover the Hubble law. There's the X factor. There's the distance for these different galaxies. You recover the Hubble law and the correlation is 93%. I recover the Hubble law and I get 110 kilometers per second per megaparsec. The periodic redshift is another Halton-Harp discovery, if you will, in that the redshifts appear to be somewhat periodic. This is an elliptical galaxy in a galaxy cluster. I plot as 0 here where it is, and then I look at the other galaxies in that cluster here and note the redshift of them. And this is the angular distance out from this galaxy. Here's the same thing for distance, but I'm using relations such as Tully-Fisher and other relationships to find distance. Now you know these two distributions do not look the same. So galaxies beyond the elliptical galaxies are having their redshift reduced to get to here. Galaxies closer to us than the elliptical galaxy is having their redshift increased to form that kind of a structure. Now, you'll note that some models, such as the bubble model, which suggests that the Earth is at the center of the universe, or the finger of God kind of model, is explained here because our redshift that we measure is along our line of sight. If we change our line of sight, this will remain the same. So it doesn't matter where we are, it's always going to be along our line of sight. Hence, we're not the center of the universe. But it is an effect that the STOE has explained. The Pioneer anomaly. All 10 anomalous characteristics, not just the one of accepted physics, is explained by the STOE. The Pioneer anomaly is measured as a blue shift in the radio signal. It is not measured as an acceleration. It's measured as a blue shift. There's my paper, 2006. The universal equation is applied. It considers the masses of the sun, planets, and with Saturn's moons, and the source galaxy in our galaxy. All other sources, things, and matter provide a constant level of plenum density. The STOE model, like with galaxy redshift, the universal equation causes a frequency shift in the radio signal from the spacecraft. This implies an Earth direction of the anomaly. All other models suggest a Doppler shift, like the accepted model of galaxy redshift, hence the acceleration terminology and the assumed sun direction of the anomaly. The equation for the C is, as before, I take two of the constants set equal to 0 because these are galaxy distance oriented. So for the Pioneer 10 spacecraft, this is the data. The data is sampled over a 10-day period. Now, this is a little long because I calculate my equation for a given hour and minute of a day. So I look for the data at the beginning and at the end, and hopefully the data point will be in the middle. This is for the Pioneer 11 spacecraft, data versus my calculations. The correlation coefficient is 93%, which is very good here. The cosmological connection. One of the 10 characteristics is noted as a cosmological connection, for which the standard model has no explanation. Here I apply the distance versus that uppercase X factor noted before. You can see the data is very good. There's the distance, there's the Hubble constant. I calculated 106 kilometers per second per megaparsec. The galaxy redshift and discrete redshift are the same phenomena as the Pioneer anomaly. The reason for the cosmological connection is in the universal equation. You remember that those things are proportional to the inverse distance, the inverse radius. And that's what gives it the cosmological connection. So predictions. I wrote the paper in 2006. In 2006 and 2005, there were several models as to what could be causing the Pioneer anomaly. So the Pioneer teams started to look into this, and they looked into it by looking at the data of the Pioneer 10 before they detected the anomaly. It was a different computer back then, and so they had quite a bit of work to do. They finally published their data in 2009 and 2011, and what they found was that the flyby encounters were present but insufficient to detect the anomaly. Several of the models suggested the anomaly started with the encounters. The STOE agrees with that. Secondly, they said the Earth-directed anomaly was preferred. Now, this to me is kind of interesting. The data said it was Earth-directed, but the standard model at this time was that the anomaly was caused by the heat in the spacecraft, a thermal reason. So to say that it is preferred or to say that it is directed to the Earth is actually a rejection of the standard model. Secondly, the STOE has a decaying anomaly, remember the 1 over r kind of relationship, 1 over distance relationship. And the thermal anomaly explanation suggests that there should be a constant level of acceleration for the spacecraft as long as it was being used. The accepted model is one of a temperature effect, which is because of the use of the electrical power spacecraft. The New Horizon mission was originally planned to investigate model differences by shutting down during the mission and then let it go for an extended period of time. Now, this part of the New Horizon mission was abandoned, because here we are later on, around 2008 or so, when the New Horizon was about to fly. Most of the models had been abandoned except for the temperature effect model. That was the only remaining accepted model. So the only thing that that test could do would be to reject the accepted model. So it was abandoned. They didn't do the test. Planet 9. Another prediction found in the Pioneer paper, which noted the orbit of Pluto was elongated with aphelion directed opposite to the source, like the RC cause. No, okay. Planet 9, nowadays called Planet X, is a hypothetical mass in the Kuiper Belt that causes the trans-Neptunian bodies to have an unexplained, long, elongated orbits. These orbits seem to be elongated in the direction of Orion, which is opposite from us than Sagittarius A is. So the STOE suggests Pioneer anomaly and the hypothetical Planet 9 phenomena are linked to a common cause, the source being at the center of our galaxy. The key to the small is what is a photon, wave or particle, and the diffraction and interference experiments that have been observed. Some experiments do suggest a particle model, such as the photoelectric effect. If the photon is going to be a particle, then it has a huge problem. The huge problem is coherence. Young's experiment, which was a double slit experiment, was taken to suggest wave-like light because in the early 1800s it seemed the only explanation of coherence was waves, and this then became the stumbling block. In 2003, the Afshar experiment rejected the Copenhagen and other interpretations. That's the wave-particle duality thing. The STOE explains how coherence occurs for particles, and that's what we're going to go into. The transparent mask experiment, which we're going to go into, also rejects all wave models but the STOE. The STOE developed a CROI computer simulation program which produces coherence, interference, and the experiments that reject the wave models of light. Coherent light is, by definition, light that produces a diffraction pattern on a screen after passing through a slit or pinhole. Coherence is obtained by light by going through a pinhole, which is the first mask in Young's experiment, by light traveling a long distance, such as from a star, as seen in the array disk pattern in telescope images. That's what Newton used, and from a laser, that's what I use. This is the STOE model of a photon. It is Hodge, structured in a column, held in a column because of the plenum, and that these things are actually small magnets, north-south, etc. They move in a direction with no surface area, that is to say they move that way. And as they move, they cause waves, just like a boat going through water, in the plenum. Each one causes a wave. Now the math here is the same as the linear array of dipole antennas. It's been well developed, you can look it up. So these things are like dipole antennas, and they form a wave in the plenum. The plenum wave goes out, rebounds off the atoms in the mask and the screen, except where there's a slit. No rebound waves from the slit is how the waves then help direct the photon where it has to go onto the screen. This is what one photon does in the plenum in its direction of travel, which is here. It reduces the plenum density considerably. The math, that is to say the linear antenna array, produces other low points in the plenum density, and I've labeled them A, B, C, and D. I start with photons positioned randomly and traveling in the same direction in the computer simulation. The Bohm interpretation held that each photon has a definite position and momentum. However, the Bohm interpretation had a problem with diffraction and interference. That is, it required a pilot wave, but he didn't know the origin of the pilot wave. Now the STOE looks at each color of a photon or of light causes a different minimum spacing on the mask. So a different energy causes different momentum, but that means that the photon must be the source of the wave. So I do the simulation. I've labeled the different directions here from the previous graph. These are minima. You note the photons are lining up along these axes. Now, if you place a screen and put a mask hole here, you'll see there's photons, avoid, photons, avoid, photons, avoid, etc. So we're going to do that. These dots that you see here and up here are where my simulated photons go. And on top of that, I plotted a Fraunhofer equation plot on top of that, and you'll see that the equation is very good match for where the photons go on the screen. You'll note that between the two first minima on either side of the peak, roughly 80, a little over 80% of the light is supposed to be in that, according to Fraunhofer, and about 80% of my photons in the experiment are in this zone also. It's a very good match. Another thing you can do with a computer simulation is trace one photon at a time through the experiment. And then kind of here's a bunch of runs. Each one is one photon going. The photons coming in tend to go towards the upper end or toward the mask. Now this has been noted by experimenters, and that they have seen that as light approaches a lens or the mask, that they do seem to deviate their path very slightly just before entering a lens. This is known but unexplained. The other thing you'll notice is it appears that close to the slit there are more photons going, with fewer going in the center. This also has been known as brightness ever since Young's time. The ones passing closer to the upper edge of the slit are directed opposite the center line of the experiment. So we then have the center peak and the diffraction fringes. The simulation produces a very good fit for actual results. And here you can see the program is discussed here. This is the transparent mask experiment. A laser, an opaque mask, which is here, and then a glass plate, which is then going to have a slit in it. And then we're going to look at the image. Here's the paper. The fourth step is to put a nail between the mask and the glass plate. And this nail is going to block the central maxima peak. So here's the results. A is without glass. That's the diffraction pattern from the first mask. I put a glass plate in without a slit, and you see it's the same distance measurement between the minima. Then I place a slit in the mask. Now the way I do this is I just take two pieces of glass and put them close together, about a 0.5 millimeter or so. And you get an interference pattern. And there's a little expanded view of this area right in there. The fourth step, as I noted before, is to place a nail so that the central maxima disappears, is blocked. And yet the interference pattern is the same. That is to say, if you measure the distance between the minima and the number of fringes, and that, you get the same in both this and this. Now, the nail can't be causing this. Certainly there's no light going through the slit, but the nail we've added can't be causing this because the minima distance are the same. Okay? The same as up here. See, that's 14 millimeters. So from here to the center of that is 7 millimeters, and that's what we measure here. The nail can't be causing it because the nail is further away. And distance here does influence where the minima occur. So the nail is not causing it. So the slit must still be causing this interference pattern, but yet no light through the slit. That's what rejects the wave models of light. That is to say, the only way you can sense that slit there is to be according to the STOE model. There's a trick to placing the nail. If you place a nail in the middle of the light, you will get a diffraction pattern in the back of the nail. This is well-known physics. If you place the nail such that the edge of the nail is right at the first minima on either side, there will be no diffraction pattern behind the nail. These are other papers. I discuss inertia and find that the mass inertia of matter belongs with the plenum and not with the Hodge. The STOE explanation for ether wind, I discussed the Miller and the Michelson-Morley experiments. The reason I label it the plenum and not an ether is because the ether models assume that the ether can have a wind. The plenum cannot have a wind, for it has no Hodge characteristics. The STOE model of the electron spin 1/2. This is the Stern-Gerlach experiment. You'll notice that an electron structure, which I give in another paper, includes magnets. So the Hodge are magnetic, the electron is magnetic, and it's the magnetic electron interacting with the magnets of the Stern-Gerlach experiment that gives the result of the experiment. It is not spin orbits. Spin, the word implies some kind of rotation, angular momentum, and it is not a spin, it's magnetic interaction. I look at electric charge. DeSangro in 2012 measured the speed of a Coulomb wave to be very much greater than the speed of light, and therefore I place it as a plenum effect. The relation of the Ampere's law in the Maxwell equation is the Ampere law is wrong, and this is an experiment which shows it's wrong. Here's another one, does the same thing. This one takes a look at magnetic fields in Maxwell's equation, and it concludes there are two types of fields. One is permanent magnets, and the other is from current. So that Maxwell's equation treats them as the same is incorrect. Here's a structure that I use to evaluate magnetic field strengths of magnets. It's got an upper support which moves vertically. The lower support, I put another magnet on, and it's directed to a scale. By moving this up and down, I can plot force exerted versus distance. There are 5 papers. This one came about because André Michaud published a paper where he looked at repulsion of magnets. I was intrigued, so I did my own with my own experimental fixture, as you saw, and saw things which suggested to me that the magnetic field may actually be a gravity field, only it's very weak. I looked at particles in that structure experiment, and I looked at electromagnets. Electromagnets do not produce the same results that permanent magnets do in that experiment. Then I looked at atomic structure. The current model of atomic structure has a problem. They assume the electrons are in an orbit held in place by charge going around a nucleus. Well, that means the electrons are under constant acceleration. That should emit radiation. It doesn't. No radiation has been found, and so that has been the fundamental problem with current model of atomic structure. Now I notice that when an electron changes orbit, it emits or absorbs photons. And with that, people have been attempting to figure out how an electron absorbs or emits photons when changing its position relative to the nucleus. Well, in my view, that it emits photons implies to me that photons are part of the structure. And going from a larger orbit to a smaller orbit, you're emitting a photon, which is part of the structure. And that discusses what a magnetic atomic structure can be. In the final paper, magnetic field evolves to be the gravity field, and here's how. This is a plot of the data in the final paper. You'll notice that there's two different structures of magnets here, and the two different structures supplies that there is a little gap here in the strength of the poles. One pole is slightly weaker than the other, and there's a difference here. And this is how it would work. If you have a high plenum density on this side, low plenum on that side, the magnetic streamlines are like that, and this is like you would find with iron filings on a permanent magnet. But some of these streamlines on the zero plenum density side do not terminate on the other side of the HOD. They just go on, and this then becomes the gravitational field. Okay, this is pretty radical, and I'm not really comfortable with it, to tell you the truth. I would like confirmation. Can somebody else do these experiments and see what you think? Especially someone in the southern hemisphere. I'm in the northern hemisphere. Maybe what I'm detecting is northern hemisphere related. Other recent speculations, the magnetic field can also cause the strong and weak nuclear forces. That is to say, the magnetic field is the one gut force. Except a fractal self-similar principle allows us to model the strong and the weak, as that paper shows. Because life is part of the universe, survival is the only moral goal of life, and a scalar theory of everything model for steering humanity's growth. Thanks, folks.
Okay, I know I was muted. Everybody's going to yell at me. Well, that was absolutely fascinating. I think one of the things, let me bring up John here. And let's see if I can unmute him here. Or is he stuck again? Oh, there he is. You're muted. I can't unmute you for some reason. There you go. Well, thank you so much. I mean, it was, there was so much in there. It was pretty amazing. Congratulations on your work, especially on looking at real data. And a couple of things that are really striking to me about your theory is how you are looking both at the macro and micro scale, something which you totally correctly identify as not being looked at in mainstream, where they basically say, oh, there's another force. Oh, there's another force. Oh, there's another. In fact, I just saw another article about a fifth force. So a couple of simple questions. HOD, H-O-D, what's that stand for?
Originally, it was YOD, which is a Hebrew letter, which is in their tree of life. But in doing the PDF or latex, I found I couldn't reproduce the letter YOD, so I changed it to HOD.
So you just named it as a name. It doesn't stand for anything, right? I mean, the letters don't. It's not like high object density. I'm just making something up. It's nothing like that, right? It's not an acronym.
No.
Abbreviation. I'm sorry. Yeah.
In the Hebrew tree of life, each letter stands for some concept.
Right.
But that's way aside.
Sure. But I mean, people will have that curiosity. I just thought I'd ask that. Also, you had mentioned a number of things about redshift. One question I have for you: Big Bang, is that something your theory supports or doesn't?
Does not.
Okay, and why doesn't it? I agree.
Well,
I don't think
needed.
it's not needed. Okay,
It's not
so
needed.
okay.
If you look, what's going on here in sources is almost like continuous bang, meaning it's continuously putting matter and stuff into the universe,
Right.
and still is, and has been for billions of years. And that, by the way, is the quasi-steady state cosmology view.
Right. And another question: Does the universe go infinitely out, infinite in time and space, in your theory?
There's that infinite thing again.
I mean,
Infinity,
yeah. Go ahead.
yeah, infinity has been kind of around in standard models for a long time, centuries anyway. But the problem with that is it's always kind of something you fall back on because you can't think of anything else. So even the quasi-steady state cosmology had an infinity, meaning you created stuff, but then what? Well, it kept going forever, out. So in adding a sink, what that does is it makes it possible to have a universe that is Euclidean and bounded, meaning there's an edge.
Okay. Now, so you don't have a problem with having a finite universe then in your model, right?
Oh, no. In fact, actually it would be preferred. However, I know that there has been no evidence at all that the universe is actually infinite.
Right. Well, I don't know if we could get any evidence of that because it's measuring infinity is a long way. Okay.
Well, that's not quite true.
Okay.
I accept the self-similar or fractal principle. And that means if you look around us, and our scale, you'll see that everything has a beginning and an end. Therefore, the universe has a beginning and an end. Now, when you look around, you see, say, trees or rocks and stones, and they all have a bound, meaning there's an outer edge. So why shouldn't the universe have an outer edge? The self-similar principle, if you accept that, says there should be. But anyway,
Right.
That's going on,
No, I that's very interesting. I also thought it was extremely interesting on your assessment of what is considered the wave particle duality problem. You had, and to get into that, your Hodge, you say are two-dimensional. What do you mean by that? Because to me, I can't see a two-dimensional means there would be an infinitely thin something, or I'm not sure. What do you mean by that, 2D?
Just that. Meaning
So
I view them as disks, but I have a problem here. To figure out whether or not they have a third dimension, meaning a thickness, would require some knowledge at a very small level, meaning smaller than a proton kind of level. And I just didn't want to solve that issue. So what is required is that light, meaning a column, has to be able to travel through the plenum for an extended length of distance. And the only way to do that at the highest speed possible, no, not at a constant speed, but at the Lorentz ether theory kind of thing, at the highest speed possible, you have to have no surface area in the direction of its travel. And that's why zero. But I'm a little uncomfortable about that, but then I see no way around it.
right. Now it's interesting because most models are either like particle models without an ether, or an ether model without really any particles. Maybe they're standing waves. But you seem to have even something different from that. You said that plenum is not the same as ether. Can you maybe give us a little bit more detailed explanation about what you mean by that? Because what you're saying right there, what you were just saying, is that if photons are moving through space, they're moving through the plenum, then if they have some type of three-dimensional shape or form, then they would slow down, and how could they travel so far? Whereas it seems like plenum to you is more of a very much smaller local effect than, for instance, with an ether effect, where you have a star that would create a wave in ether that would then travel through collisions until it gets to 10 billion light years later, it comes to our eye or telescope. Maybe you could explain that difference between the plenum and the ether a little bit more detail.
In ether theories, at least all that I've seen, they always assume that the ether has some kind of wind. And that means, like wind on a sail, means matter that then collides with the sail. When you look at their photon models, they always assume that the photon is somewhat spherical. But take any spherical object and send it through a wind, like the Michelson-Morley experiment, and you will get resistance. Well, that can't be. So the plenum is without gravitational matter, but it does have inertia. It has to have inertia to support wave action. But the plenum then is all throughout all space.
Okay, and so light is not a wave through the plenum.
Yeah, here we go with Copenhagen again. Copenhagen is wave or particle, depending on your experiment.
Right.
The STOE is wave and particle. Wave in the plenum and a particle going through the plenum.
Okay. So light is waves through the plenum, and then it just depends on which part of what you call light. Is that it, or
no? The light is always the Hodge structure.
Okay.
Right. Particles are Hodge structures, but as it travels through the plenum, it generates waves in the plenum, so that the diffraction effect or the interference effect is matter, meaning the photon, and the wave in the plenum influencing where the Hodge go or where the photon goes. Note the similarity with general relativity. The matter influences space, Hodge influence plenum, and plenum then directs the Hodge.
Oh, okay. I'm starting to get a picture in my mind about that. Again, if you have any questions or comments, please, in the comments you put, I think I have that there. Oh, here we go. This is confusing, so I want to ask, what separates the scalar theory from every other theory? Well, that's kind of a big, giant question in some sense, huh? I guess you've mentioned those already, or is there some more general overall idea you could give a person who wanted to know more of a generalized answer to that question? Or
Well,
is that
in the
just...
first 10 minutes, we go into the postulates. But what separates it is that it envisions that there are two things in our universe, not one or not more than one, just two, and that those two things emerge into everything else in the universe, including life, etc. So, thirdly, I would add that no other theory that I'm aware of since Newton attempts to look at both the small and the big,
Right. Understood. Yeah. And let's see, what other question? Oh, yeah, I thought it was really interesting too, because there are sort of more modern models out there that are being built today, and they do try to do the same thing you're doing, which is trying to reconcile between the small and the large. Nothing in the mainstream. That's just to how do you say too problematic. I don't even know what to really put a word there.
I'll go.
I mean, except trying to untangle their problems is just not worth it. So you did mention that one of the problems, which I agree with, my father and I, are working on a model called the particle model. We absolutely agree. This idea that somehow an electron going around an atom is something that causes its movement, causes a photon to appear, and that photon not to be somewhere inside this. Where's that coming from? No, mainstream science never says anything about that. Maybe you can. You did mention that it must emit radiation, is what you were saying, but you said that your model explains that problem. So maybe you could elaborate a little bit on that. I got it, but it went by pretty fast.
Well, when the original idea of electrons around a nucleus was formed, and this is maybe almost 100 years ago now, the electron going in an orbit implies that it's under constant acceleration. Charges under constant acceleration should emit radiation. I mean, that's general Maxwell's equation. But they don't. So that's been a problem with the atomic structure models all along. Now, the backup to that was de Broglie, and then later on, the quantum mechanics viewing it as clouds and all, but you're still left with the fundamental problem. There should be emitted radiation normally, but it's not observed. Now, this business of the photons coming out, the attempt that I've seen more recently is to say, well, if there is a photon coming out or going in, then it must be associated with the electron. Now, how do you put that much energy with an electron? And, and that's been the problem now.
Right.
So I say, look, they're separate things. And so you get over the accelerating electron not emitting by saying it's held in place by a photon rather than that is going in an orbit, meaning no angular momentum.
Okay.
And of course, that's the same thing that you run into with the Stern-Gerlach experiment and the spin issues. It's not spin; it's magnetic.
Mm-hmm. That's another question I have. But let's get to some other questions here from people in our chat room here. It says, Franklin Hughes says, what is gravity in your theory? What causes the electrostatic force if it is different?
Gravity is like some other ether theories. It's the gradient or divergence of the plenum density. This is Newtonian. What causes the electrostatic force? It's all magnetic.
Okay. And I guess the follow-up question to would be, what then is the magnetism? Is that just a force that's there? Is there any explanation for magnetism? Because I can tell from your photon model, you have Hodges being held together because they're dipoles and they're magnetic, correct? And
magnetic, yes.
Right. And then the question would be is what is the magnetism? Is that something just that's there, you don't explain, it's just is a fundamental part of the universe?
That a Hodge is magnetic is one of the postulates. We don't explain it, just that's the way it is. But what magnetism is, it's a high plenum density on one side and a low or zero plenum density on the other side. Which, I don't know, I've given some thought to the idea that a Hodge is actually a discontinuity, mathematical discontinuity in the plenum. But that's another paper.
I tell you, I just got lots of other questions. I mean, what I really enjoy about looking at different theories, because people a lot of times, if they're working on your own theory, and that's what you do, obviously, and worked a long time on it, and you're trying to get people to take a look at it, and it's out there for people to look at. One of the things I think I find fascinating, and I love looking at new views of the universe, new models of the universe, is the experiments that people find, is the data that you find, is the things that you explain. And one of the things is that you were looking at, which I thought was really great, because my father and I were working on the same problem, is the diffraction, and where you have the single slit, then you have this followed by a single slit in glass, followed by putting a nail in front of that. Now, a couple of questions. Did you do that experiment yourself?
Oh yeah.
So,
I'm the originator of it, I think.
all right. Well, do you have any documentation of what you've done?
Oh yeah, that's a paper that's published. In the video, I think I gave a reference for it, I
Right.
think.
Right. Okay, but you did them yourself in your own home? Is that what you did?
Well, yeah.
Okay. And
Yeah.
okay. And then did you, in your paper, did you have any photo setups of how it was done in the actual setup?
Yes, that's in
Okay.
the paper. And one of the videos, the thing that talks about 3 amateur experiments I did,
Right.
is a video on my YouTube channel that actually shows the experiment being done.
Okay. Well, let me see if I can. I should get that YouTube channel up there for people to take a look at. So let me remove this here. It's not screen. And so yeah, you have a YouTube channel. The YouTube. I will put that down in the link after this. After we're done with this presentation and talk today at noon our time, I will be sure to put in a link to obviously the video that you have, and it also will get you to your YouTube channel. Now you've done that just recently, is that correct?
The experiment?
No, I mean the YouTube channel. I'm sorry, just say it.
Oh, I don't know. I put that up starting maybe a year ago.
Yeah, so it's fairly new, so a lot of people may have not seen it. So that's something people could take a look at, and I think that's just fascinating because it brings up more. One of the things my father and I found, there wasn't a lot of variations or experimenting with the diffraction or double slit or even single slit experiment. There was some out there, and I think part of it is because people don't have a model for it, so they're sort of lost as to what to even say about it. And I'd like to know, what was it that caused you to do that different experimentation with what drove you to doing your own slit experiment?
Well, nobody else was doing it. Now, I come up with a model back in around 2010. I published a paper around 2012, if I recall correctly. But it was pretty radical, as you saw. So the issue comes, how do you distinguish my model versus the standard accepted model? And that then is the experimentation, is
Right.
to find some experiment that will show you that my model is right and everybody else's is wrong. I mean, that's what experiment does. It's got to reject everybody else's and accept or not reject mine. The experimentation began around 2015 or so. And there are many of them. You'll find that on my intellectual archive papers. But there was some conversation about that, in that some people would write to me, and we had a long conversation with a couple people that found a wave model that could explain some of the experiments. Now, they had to assume several additional postulates over and above the Huygens postulates to do it. But, that doesn't seem to faze the folks that are in the standard theories. So I found one, the transparent mask, that they can't explain. They can't explain. So
Yeah, that was one of the. Yeah, that was it, and that was one of the interesting things that we were also looking at is, both models, either just an ether model or a photonic model by itself, has problems. They both have problems, And I think that's what you saw, and then you came up with your own experiments, which is absolutely fantastic. I'm sure my dad and I will take a look at those because we're still looking at how to explain that. Here's another question. I think it's you've sort of answered it, but I think maybe a more detailed answer. It says, how does the gradient generate points? And I'm thinking what you were is I'm thinking this is what back when you were talking about the plenum. So if you have the Earth sitting in a plenum, it's the ether is supposedly moving, I guess, or a wind or something like that, where you're saying the plenum is somewhat just sitting there. Now, is it the case that mass just displaces it so that there's more plenum near a mass, or what is that?
Well, you asked the question earlier about what the thickness of the Hod is.
Mm-hmm.
And this is one of the reasons to say it has no thickness, is that the plenum is not displaced by mass, that is to say, Hods. And what mass is, or bodies are, is a plenum and Hods. Remember, the photon there is a column.
Right.
Well, an electron is a group of Hods in a particular structure, you see.
Okay.
So what the gradient is it's simply taken that mathematically the gradient is the difference of plenum on one side versus plenum on the other side of the Hod.
Right. Okay. Here's another question again. It's how is gravity Bush? No problem. You okay? Hey, happens on live all the time. So how this person is asking the question, how is gravity divergent?
I'm not too sure I understand the question. Divergence in mathematics is a specific function, and it's the difference from the gravity potential, the plenum potential in one place versus another.
Mm-hmm.
I mean, divergence is just simply a vector operation of gradient.
Right. I think one of the things that is totally unique about, if I were to, just off the top of my head, looking at, because I know lots of models, maybe more models than most anybody on the planet, because I actually look at them of interest. Even though my father and I are working on our own model, I still have absolutely great interest in other people's models. Is that you have the wave particle duality solution in your mind is really sort of like having the photon, a particle. It's just, again, I'm just going to use them in broad sense, okay? And you have a plenum, which is sort of an ether-like thing. It's not the same as what's considered to be traditional ether. And with those two, you're able to explain things that mainstream science cannot explain. So is that sort of a good characterization?
Well, you're getting kind of philosophical. The idea is that we have a small set of assumptions, postulates. And from that small set of postulates, you then derive everything in the universe. And I call it emerging, So Hods get together with a little bit of plenum, and next thing you have photons. Photons get together, and you got neutrinos. Neutrinos get together, and you got electrons, etc. At least that's the idea overall. Now, the thing that makes this model versus other models acceptable is that currently standard physics has cosmology with a whole bunch of assumptions, far more than I have.
Sure.
And then they have particle physics, which has even more assumptions than I have.
Yep.
And so the goal here is to get this model with its few number of relative assumptions and derive everything. Mm-hmm. Now, the way you do this is very simple. You take a look at what the constants are, and then you apply the postulate of feedback loops along with the postulate of fractal universe, and everything should fall from that. Okay. But this is a very few number of postulates compared to what's in both worlds.
Right. No, I understand. I get that. So it's basically what they call Occam's razor. It's a much simpler model with a lot less postulates or assumptions, whatever you want to call them, and you can get the same thing, which a much simpler model. This is just a clarification. It doesn't mean you have to comment, but I think Bob and Ann, that's the name of the person's name online, says gravity is not a force, it is the opposite of force, so it cannot be divergent. Now, again, I think we don't want to get necessarily into what that is, because what people mean with what words they have can sometimes, we could get just into a word salad of trying to understand that. But I just wanted to put their comment up there so they have there. I do have some people in the green room. I see a hand up that I'm going to bring up, and some people would like to make comments or talk to you directly. I see Bob Gray put his hand up there. Hey, Bob, you're muted there. Let me unmute you. Can I do that? No, you have to do that yourself. Unmute yourself. There you go, Bob.
You go.
Welcome.
Thank you. Thank you, John, for the presentation and your work. Very interesting. Did I hear you correctly? Did you say that there are two different kinds of magnetism, one due to a magnet and one due to a charge in motion, and those magnetic fields are not the same? Do you have an explanation of that, or papers, or what?
Well, there's a couple of papers on the Maxwell equations. One is the Ampere law, and the other one is the one you're addressing. They're on the Intellectual Archive, if you see it. But generally, in Maxwell's equations, there's that factor B that occurs in a couple different equations, and they're two different B's. That is to say, they have different effects. One, you get the B from the current flowing, if you want, and the other one, the permanent magnet B, is generating a current.
Mm-hmm.
I mean, this is just saying that those B's really should be two different numbers rather than one.
And this is a paper that you have, or is it?
It's on the Intellectual Archive.
Okay, super.
And yeah, the experiment is not a theoretical. It's an experiment, not a theoretical issue.
And in your paper on this Intellectual Archives, you give the reference to that paper for the experimental?
Yeah, it was in the video.
Right.
Yeah.
Okay. Thanks so much.
Yeah, thank you.
Okay, all right, great questions. Now, anybody else in the green one want to come up and make a comment? Okay, I've got another person. I usually, just for people to understand, I usually try to get to the chat first, because there's been a lot of chatting going on, and then near the end, I usually get to the people in the green room. So that's just to give you an idea. So I'm going to bring up Ian Cohen, who is from Ireland. So got that right to this today. So Ian, welcome, and you have a question or comment for John.
Hello, yes, David and John. My question is about your reference, I think, to the Biot-Savart law, which I think you dissented from. J.P. Wesley, whom you may be familiar with, has looked at this, and he claims that that is problematic because it doesn't conserve energy, nor does it satisfy Newton's third law. Now, I presume, therefore, that you have some problems with the Lorentz force law. So you might want to say something about that. But one point, I was a little surprised that you also said in that connection that the Ampere force law was problematic. Whereas I thought that if you criticized the Biot-Savart, you might have said, well, I prefer the Ampere force law, instead.
Well, this was experiment again, that rejects the Ampere and the Biot-Savart law. Now, the thing that's rejected is that the idea that it's a cross product of the current versus the point, right? Meaning there's a sign of the equation. Instead,
in the Lorentz force law.
Say again?
As in the Lorentz force law, presumably. You have the same sort of...
Right. That's
V
right.
cross B. Yeah.
They also have a cross product there, which means that current anywhere along that line should be influencing the magnetic field at some point. And that's not the case. And that's what the experiment shows, that it's only perpendicular to the rod. The experiment is that I take a rod and I run current through it. And then I put a magnet close to the rod and measure the magnetic force on that magnet. And what you find is if the current is not flowing directly over the magnet, there's no magnetic field. That is to say, the cross product is wrong.
So the other part of my question was, I understand what you're saying, and that comes into Biot-Savart and Lorentz, as I say. But surely it doesn't come into the Ampere force law, which doesn't have that. In fact, it has the dot product of the current elements.
Right, but dot product doesn't work either.
Not for the reason you've just given, though, because in the same direction it wouldn't, give that problem. Presumably,
It's
at right angles, it would.
Yeah, at right angles, it's right, but not at any other angle.
Oh, okay. I'll have a look at that. Thank you very much.
I might add one other thing. You'll note that in radio antennas, where they radiate electromagnetic energy, the formulas that people deal with in calculating intensity at some distance is always perpendicular to the antenna. They assume that it's radiating waves perpendicular to the antenna. And that's what I'm saying here. That's what goes on.
So you think one should be looking at all the directions, in a fuller analysis?
No. I agree that the practical implementation of this business of current going along a line, the practical implementation is actually correct. It's the theoretical implementation when you start. Yeah. It's a straight right angle to the current flow, and and almost all practical implementations will do that.
Okay, very, very well. Thank you very much.
Yeah.
All right. Very interesting. Very interesting. I think one of the most fascinating things, most people who come up with models don't do experimentation or don't look like you said to find experiments that would show your model explaining the universe better than someone else's, or explaining something that they can't, or something that you would feel rules them out. And that led you to do the experiments yourself. Now, that was with the slit experiments, what you call the transparent slit experiments, what you showed, of course, in your video at length. And that is where you claim to filter out other models that people have, either whether it's an ether model or a photon model or the mainstream model. Is that a correct reading?
Well, yeah, it's straight Popper.
Okay. All right. So we have other people in the green room. Anybody else want to come up and make any comments, or I don't see anybody in the sense. Let me see here. The green room is available. Actually, we do have seats in there. So if you want to come on live, you can. All you do is go to live.naturalphilosophy.org, and we will come up in the green room. We have room for 10. We have 1, 2, 3, 4, 5, 6, 7, 8. We still have a couple of places there. I know there are other people there. So if you do want to come in the green room, either put it in the private chat, and I will bring you up, or we will wave to me if you are there with your video. So let me see if we have any other questions here. I guess one of the questions questions to you is, you've been working on this for, it sounds like, at least 2 decades pretty vigorously, and you have published, like you said, you're getting information out there published. But you also made, at least in the bio that you sent me and the thing that I read to people, you mentioned that you started talking at some type of community college. Is that correct?
Yes.
And why don't you tell us a little bit about that? Because that's kind of, again, you were rejected by mainstream publications. They maybe first accepted, and you had mentioned that. But that seemed to be on your own initiative and had opened up a classroom. How did that come about? Why don't you tell us a little bit about that part of your work?
Well, it was just pursuing an interest. I'd been retired, that is to say, not working for anybody for a number of years, and the community college would like some input, so I did it. I mean, it's for a few years. Taught, cosmology was one. Actually, a couple different classes, but generally of a cosmology nature.
Yeah, but I guess what I'm getting at is so many people do work outside. Even my father gave a talk this week to a group outside his normal science realm. I mean, that is still fascinating. I mean, did you go there? When you were talking about cosmology, did you mention about the work you were doing, or did you keep it mostly about other things other than the STOE?
Well, the idea of the cosmology class was to teach what was standard models at the time, not what I was doing. So I usually did mention in about one half of a session what I was doing, but that was towards the end. Mostly it was, what standard models are.
Right. Now, was it the case, because I know of another teacher, a friend of mine, Luis Sarabon from Brazil, who teaches at the engineering school near Rio de Janeiro, and he was teaching classes in the engineering class on science, and some of those would include even topics like cosmology and the Big Bang. One of the things for a while and for many years was required that students also look at the pros and cons of something like the Big Bang, instead of just basically telling everybody what mainstream science talks about the Big Bang. He would then say, okay, a requirement for you to receive a passing grade is to show the pros and cons of what you're looking at. So I don't want to say, the Big Bang's accepted, anything that's against it, or the small problems. I want you to go and find people who reject the Big Bang and put their arguments there, and then make an evaluation on your own. Now, was that something you were doing? Were you presenting in a way that a normal person who would present about cosmology wouldn't include perhaps things that you would, for instance, Houghton Arp's work, or did you include things that you think a normal cosmology class wouldn't have?
Well, Arp's work was presented, but you understand that was near the tail end. Generally, I would start with the Greeks, go through Newton, and then into the 20th century.
Right. Did you at any? I guess what I'm getting at is, when you're in a position like that, and you are a person who's a critical thinker who has some critiques of cosmology, that you would be able to also enter and talk about things that I don't think Houghton Arp is a standard presentation in most cosmology classes. Do you think?
Well, he was minimized, meaning I only talked about him for maybe a half hour or so. But I understood my job differently. It was to present what was standard. Remember, this is junior college. This is not advanced.
Right.
And the job is not to go off in all different directions, but to kind of hold true the average college student, not in physics, is not going to see that stuff.
Right, of course.
They're just going to hear what is available, and to have them sit there and say, "Oh no," that gets him into a hot water.
So you never got yourself into hot water, or a student coming after class saying,
"Oh no."
Okay.
No, I mean that's not the place for that kind of thing, in my opinion. I'm going to get into the philosophy a little bit about that, and okay.
And I think it'd be interesting, because again, I think your model, congratulations, very intriguing. I think it's very thorough. And I think it addresses many big problems in mainstream science. But the question becomes, where is this supposed to be taught? One of the things that was interesting is one of the guests we've had on, it was actually received a Lifetime Achievement Award, was Dr. Gerald Pollack from the University of Washington, who found a fourth state of water H3O2, and it actually is, it's there. It's what causes meniscuses on water, and it's fascinating. It's absolutely incredible work. But he can't really teach. He can only go so far without being, sort of even ridiculed for even something that he has proof of. And one of the things he talks about is, and we talk about quite a lot, is that universities should allow people and allow students to say, no, I don't agree with the Big Bang. I want to look at it. I want to write a thesis on that, and here's what I want to do, much like your work. Now, do you think, you said, well, that's not where it normally happens, but where should it? Where should John Hodge, let's say if you were in your teens when you came up with your idea, I know you said you did a little bit, but at least for the work you've done in the last 20 years, if that was during your late teens and early 20s during the university times, do you believe that universities should allow for that kind of work that you're doing? It's science, for goodness sakes.
Well, you're talking about two things here. One is what should be done, in my opinion, and the other is what is. And in the junior college level, which is where I was at, your job is to present what is standard, accepted. Which, by the way, is you like Thomas Kuhn, and Thomas Kuhn is just exactly that the scientific community should determine what is accepted. So that's why I go to Popper anyway. But anyway,
right.
In my opinion, the place where you should begin entering into the different views in a particular discipline should be in the junior year in college. Now that disagrees a lot, because a lot of people will tell you that it begins at the graduate level. And some people even say it doesn't begin at the graduate level either. It just shouldn't be. Meaning,
well, yeah, I guess what I'm asking is, I understand what's there, but in what's there, in my opinion, it doesn't exist anywhere. We have one of my mentors.
I agree with you on that, absolutely.
But my question to you is, and the way I feel, is that's a failure in our university system. Of course, you need to understand what has come before you and understand all of what is considered to be consensus in science. But there comes a point to which we in our education system need to do what other parts of the education system do. It's so amazing to me that I'm in the software engineering area. And when you're in software engineering, if you are a student and let's say now you're in your junior or senior year and you come up with some new idea, maybe a new computer language. My friend and I did come up with a new computer language for a specific task. And that seems to be very well accepted. It seems to be okay. Even if you say there's a better way to do it, people will argue, oh yeah, but you can go out there and do it. There seems to be in other disciplines the ability to go outside the box and try something different, and it's even encouraged. But for some reason, physics and cosmology don't seem to have that as part of their psyche, I guess. That seems strange. Have you ever thought about that? Why that would be, or you just don't? Yeah, I don't. Fighting it is just impossible.
Well, the scientific community is a very close-knit community, and you're fighting all of society, essentially. So I don't fight it. I just go about my way. I publish my papers, and maybe in a few decades, if I'm right, somebody will recognize. But that being recognized is not a big part of my reward. I just like doing the work.
Oh, of course,
and those
of course.
Are going to be, yeah. And those like Halton Arp, he's a classic case of, being rejected by the society. Of course, you could go back to Galileo and see what happens when you start fighting the society too hard.
Right,
right.
Right.
Yeah,
Well, I think the other part is too is if even Newton, when I first encountered a person who was questioning, for instance, special relativity, and a mentor of mine, I went to the library and checked out every book I could on paradigm shifts, or when does science shift? When does something come along that changes science? And I was really shocked to find a book on a biography on Newton, because you hear, Newton's his work has been so pervasive and has done so many things. You never hear about the how do you say, social aspect of his work. And one of the books that I read actually said in the very end, the very last sentence, and I think in the book said, and Newton spent the rest of his time, I guess he was the head of a mint being where they made money, and it involved doing physical things, and physics was often a position of just honor. And it said he spent the rest of his time working for the mint and defending his theories to his peers. And so you don't think of Newton having to defend his theories, because in our minds we think, oh, he was totally accepted and everybody thought he was correct. It wasn't true either. It took time for him to be accepted. So it's always interesting to us and people who are doing this, who do want their work to be at least considered. I think that's a question that people have. But we are at the end of our session today, and I want to thank you very much, John. I really, really enjoyed your work and your presentation. I especially enjoyed that you put down your postulates. Many people who have models don't do that, and you did right up front, and so everything was built on that. I think your model has a lot of amazing descriptive power that a lot of mainstream doesn't. It addresses the wave-particle duality head-on, which I think is absolutely admirable. And you actually show an experiment to show why your model is a better model than other people's models, where experiment will reject other models. So my hat is off to you, sir, and congratulations. If you want to, of course, check him out on the internet. But thank you so much for today, for your presentation and answering questions.
Thank you, sir.
All right. Well, listen, I do want to, again, thank him very much for coming on and presenting. It's not always the easiest thing to come out and with a new idea and have people expose yourself to the world to that. But I think it's always worth checking out. He has amazing data, even did a new experiment. So if you have your own model of the universe, you need to look at the transparent slit experiment that he did, and to figure out, okay, what's going on there, because his claim is that it eliminates a lot of different models, including an ether model, what was considered to be a traditional ether model. So it's well worth checking out. I will later on put the links to his work below, but you can check out his work on the internet. And congratulations to him. So let's go out of here and tell you all about what our organization is and wrap this session up for today. All right, remember, stay critical, stay thinking. I am David D. Hilster, your science therapist, trying to get you to the promised land of becoming a critical thinker. Ciao for now.